Welcome to fifth in the series of lectures on simple machines. If you have survived this far, that's great. Okay, so in this video we are going to look at simple machines from a perspective of energy, and so far we have been looking at it from perspective of torque. We always say, hey, you know, your input torque is over here, is equal to the output torque. Right? So now we're going to look at it from the work point of view. So let's imagine that you have this load which is being lifted up by this quantity dl, and on this side your effort arm is moving down by distance of dE. This whole scenario can be represented in a simple picture as shown here. So this side is your input, and your input work, your input work is given by your effort into the force into the distance moved by the effort arm. So that's your effort into dE, and your output, this is your output which is on the load side. So your output work is given by your load into the distance moved by the load arm. And ideally, both these have to be equal in magnitude if your input work is equal to output work. But in real world, that's not the scenario. Your input work is usually not equal to output work. And we define the efficiency, which is, this is a symbol for efficiency. So efficiency is denoted by this Greek symbol. It is called eta. Efficiency eta is given by your output work, which is always less than your input work due to various losses like friction, heat, etc., etc. So your output work is nothing but your load into distance moved by the load arm, and this is effort into distance moved by effort arm, and this whole thing can be rewritten as L by E divided by dE by dL. And this is nothing but your mechanical advantage divided by the velocity ratio. So you can say your efficiency of this wedge, this lever is MA by VR. If your efficiency equal to 1, then we can say your MA is equal to VR. So that's a very, very special case when your efficiency is 1, and usually it's better to write this as a special case. So you can always write this as an ideal I mechanical advantage. Ideal mechanical advantage is equal to velocity ratio. So you may be better off writing IMA is VR, but remember your IMA or MA is nothing but your load by effort. So your MA is nothing but your load by effort, right? Or even IMA. Doesn't matter. We don't know what it would be, ideal or non-ideal, but definition of mechanical advantage doesn't change. It's load by effort. Okay. So now let's use this whole idea to discuss a problem, right? Let's assume that your load is here. Your load is 100 kilogram force, and your DL is moved by 1 centimeter, and DE is moved by 10 centimeters. And given that your efficiency is equal to 80%, right? So what you got to find? You got to find the following. A, you got to find what is your effort. What is your effort? What is your mechanical advantage? And what is your velocity ratio? And what's your efficiency? So take a pause and try to work out this problem. Sorry, you have efficiency already given, so you know that that's 80%. and your velocity ratio you should get as 1 by 10. Oh, sorry, not 1 by 10, 10. And you should have got your mechanical advantage as 8, and your effort would be 100, which is load by 8, which you'd have got it as 12.5 kgf. So if you've got these answers, then you're right. And let's see how we have got this. So the first thing is your velocity ratio, and velocity ratio is something which is fixed, and it can be found by finding the ratio of d by dl. And in some cases where they would have given you the length of the effort arm by the length of the load arm, you can also use that if it's a rigid bar and there's no bending at all, right? So this is clearly given to you. So this is 10 centimeter by 1 centimeter, and that's equal to 10. And 2, your mechanical advantage is given by efficiency times VR, and that's equal to, you have 0.8 into 10, and that's equal to 8. And once you have your mechanical advantage, your third part becomes very easy, because you know that your mechanical advantage is load by effort, and that's equal to 8, which implies that your effort is 1/8 of your load. If it were 100% efficient, it would have been 1/10 of the load. So here it is 1/8 of the load, so which is 100 by 8. That's equal to 12.5 kilogram force. So if you have done this and if you've got the answer, congratulations. You have understood this topic well. So the summary of this video is as follows. Your mechanical advantage is given by efficiency times velocity ratio, and this is given by eta. This is eta, and this is your efficiency. And your velocity ratio is usually fixed, and what changes is your mechanical advantage based on your efficiency. A special case is efficiency is 1, and we call it's an ideal case, and hence we say it's an ideal mechanical advantage, and ideal mechanical advantage is equal to the velocity ratio. And your load by effort is efficiency times d by dl. So we know that mechanical advantage greater than 1 is a force multiplier, and velocity ratio of less than 1 is a speed multiplier.